So we are starting now.
Yes, sir.
Thank you.
Okay. Greetings and a very warm welcome to all the esteemed dignitaries and participants joining us today. I am Kashish from Clarinet and I'll be your session assistant for today, here to ensure that we have a smooth and enriching experience together. Clarinet is proud to be India's most trusted digital platform dedicated exclusively to serving the medical community and offering a global space for healthcare professionals to collaborate, create, and engage with medical content. So, we are truly honored to be the digital partner for this special event hosted by the Jaipur Society of Anesthesiologists. And the topic of discussion for today will be PG Assembly Vaporizers. So, before starting, I request to all the participants, if you have any questions, kindly post it in the chat box available on the live session page. For which, now I would like to invite Dr. Jyoti Jain, ma'am, and allow me a moment to put your CV deck on, ma'am. So, ma'am is currently an assistant professor at Mahatma Gandhi Hospital, and her areas of interest are USG guided regional anesthesia, oncosurgery in pain, and she has also served at Ministry of JSA and faculty in various conferences and academic activities. And today, ma'am will be moderating this session. So, ma'am, I welcome you and over to you.
Good evening, everyone. It is my pleasure to introduce our chairpersons for today. Both are eminent figures in the field of anesthesiology. Our first chairperson is Mamta Sharma ma'am. She is a senior professor working at SMS Medical College. Her area of interest is difficult airway and liver transplantation. She has various publications in international and national journals. Our next chairperson is Dr. Adarsh Chandra Swami sir. Sir is Director of Anesthesiology and Pain Services at Santokba Dullabji Memorial Hospital. He has a special interest in acute pain management, labor analgesia, and obstetric anesthesia. Now I request Mamta Sharma ma'am to introduce the topic and speaker. Thank you.
Good evening, everyone. Am I audible? Good evening, everyone. Am I audible?
Yes,
Yes,
you are
ma'am,
audible.
you're audible.
Yes.
Good evening, sir. Good evening. At the outset, I thank the organizer for giving me this opportunity to participate in this webinar on anesthesia vaporizer. Understanding the vaporizers is not only important from PG examination point of view, but it is also important for our daily clinical safe practice and for patient care. Dear students, we use vaporizer almost every single day in the OT, but I think most of us would agree that it is the least understood anesthesia equipment. Its functioning is complex, and its understanding of its functioning requires good understanding about the thermodynamics, gas laws, physics, and physiology as well. So, to make this complex topic simpler, we are fortunate to have Dr. Amit Shah sir between us. He is highly acclaimed anesthesiologist from Vadodara, Gujarat, and his main areas of interest are airway management and low flow anesthesia. Sir's CV runs in pages, but to highlight few important points, he is General Secretary of All India Difficult Airway Association. He is Course Director of Fellowship of IDA. He has received many awards, including ISA Presidential Award twice. He is author of IDA 2026 guidelines. He has got around 40 publications and has delivered 300 plus lectures in various national and international conferences and conducted 100 plus workshops. So without further delay, I now invite Dr. Amit Shah, sir, to begin the session. Over to you, sir.
Thank you, Dr. Mamta, for those kind words. And as you know, I'm starting. Let me thank the Jaipur Anesthesiology Academic Foundation, JAAF, and also the SMS Medical College Anesthesia Department for inviting me and giving me this opportunity to speak about a very interesting topic of vaporizer. As Dr. Mamta highlighted, it is a very complex machine which we don't understand, but still we use it almost every day. So thank you, Chairperson, for the kind words and the introduction. Thank you, Dr. Akil. Thank you, Dr. Vanna ma'am, for giving me this opportunity. Let me share my presentation. Okay, I hope you can see. Right? Okay.
Yes, sir. Yes.
So modern vaporizer, what I'll try to do is to understand how vaporizers work, what are the technology which is there in different types of vaporizer, how they are made more accurate, and what are some of the important points, how we can avoid the problems with the use of vaporizer. So the first line is very, very important. I will be talking about various vaporizers which are brand of many companies, but we do not represent it or endorse any technology, product, or any company. Some of the images are taken from How Equipment Work website, some of the images, and these are my sources from where I have gathered this information. So now when we talk about inhalation anesthetics, okay, the inhalation anesthetics, isoflurane, sevoflurane, or any other agent comes in a liquid form. So we cannot just pour straight away liquid into patient's throat. Though ether was something which we were putting it into the patient in front of patient mouth when we started, but we cannot do it for every agent. So what we need to do is to convert it into a gas form. So we need to convert that into the gas form to deliver it into the lungs, from where it can be absorbed and go into the body and finally into the brain. So you need to convert liquid into the gas. Now, when we have to convert liquid into gas, we have to understand some of the physics part of it. So each substance is stable in its particular phase, either liquid or a gas or any solid form, at particular temperature and the pressure. Let us look at the example of water. Water at 25 degrees centigrade and 1 atmospheric pressure is stable as liquid. When you reduce the temperature below 0 degree, it converts into the solid. And above the higher temperature, it converts into gas or vapor form, which transit between liquid and vapor. So this transition from its liquid form to gas and vapor form depends upon the temperature. So that is where comes the first understanding, which is called the critical temperature. So what is a critical temperature? The critical temperature of substance is a temperature at which and above vapor of any substance cannot be liquefied, no matter how much pressure you apply. And every substance has a critical temperature above which you cannot make it liquefied. I am giving you an example of water at 25 degree centigrade, it is liquid. At 100 degree, it starts having some vapor, but at 374 degrees centigrade and above, it converts into the gas or gas form. Below that, above that, you cannot convert it back to the liquid. And that is there on the Venus. So on the Venus, the temperature is 374 degree. So on the Venus planet, the water would be in the gas form. We can look at some of the critical temperature of some other substance like oxygen. Now, oxygen critical temperature is -119. That means above -119, it will remain in the form of the gas. That is how it remains in the gaseous form on the earth. And to convert it into liquid, which we do get, right, into the liquid tank, oxygen liquid tank, which we get these days, the temperature has to brought down. That is why they are all cooled liquid tank, because the temperature inside and the pressure inside are different, and it is cooled to this temperature to make it liquid, and then when it is released, it converts into the gaseous form. Now, the gas and the vapor, there is slight difference. Gas as a substance is in gaseous form above its critical temperature. So above critical temperature, it remains in the gas. Vapor is a term which is applied to a substance in the gaseous form below the critical temperature. So above the critical temperature, like water for 374 degree, it cannot be squeezed back into the liquid. But below 374 degree, it can be converted to, some of them will convert it to vapor, and then it can be brought back to the liquid. So this gas and liquid form can be transformed below the critical temperature. Okay. It will go back and forth depending upon the temperature on which it is. So after understanding that part, let us go to the next, the vapor, which is the most important part, where our inhalation anesthetic are converted into the vapor and then taken over and supplied to our lung for the anesthesia. Now, when you look at the any liquid, the vapor formation, the liquid has various molecules. Now, if you look at this molecule, all molecules have connections. That means they have a bond with each other, as well as they have a kinetic energy. Now, this kinetic energy, those molecules on the surface can break away. Okay, they can break away and then goes into the atmosphere above that particular liquid. Okay, this molecules is something which is called the vapor. So molecules have a kinetic energy which allow them to break away from the surface into the atmosphere, and they make the vapor. Now, this vapor molecules which have gone into the atmosphere and formed into the vapor, okay, has a constant up and down movement. Some of them gone up, some of them will lose the kinetic energy and will go back to the liquid. Okay, some of them will gain more energy, will go up. So after certain period, there will be something called the equilibration. Okay, so at equilibration in a closed container, the pressure will stabilize. The molecule going in and out will stabilize, and the pressure which it creates is called saturated vapor pressure. Okay, so there are two important points. This is for that particular temperature. Okay, where at the equilibrium, the pressure exerted by vapor is at maximum for that temperature, and it is called saturated vapor pressure. Now, again, here there are some of saturated vapor pressure at 20 degrees centigrade at 1 atmosphere I have shown. The important, you try to understand this particular pressure, because this we will use later on to identify how it works. So the vapor pressure of halothane is 32, vapor pressure of isofluorine is 33, and desfluorine is slightly higher. And this saturated vapor pressure can increase as temperature increase. This is very important. So if you increase the temperature, more vapor will form, and the pressure which is created by that vapor will increase. Okay. So why this is happening? Because more molecule, because of heating, will get this kinetic energy to break away from the surface towards the atmosphere, and this will form more vapor pressure. Now, when you heat this, any agent, it forms more pressure. So temperature at which this saturated vapor pressure reaches the atmospheric pressure, it is called the boiling point of a particular liquid. Okay, it is called the boiling point. So what is a boiling point? Boiling point is temperature at which the saturated vapor pressure equals the atmospheric pressure. Again, look at the boiling point, that is a temperature point for desflurane. Okay. Now desflurane boiling point is 22.8, which is quite near to the, our average atmospheric pressure or operation theater pressure, so the temperature, which also we'll consider and understand later on when we'll understand it further. Okay. So this is a vapor pressure which is created. Now, when it is added into any container, there are multiple gases. Okay. Just say gas A, which is oxygen, could be gas B. If you are using nitrous oxide, could be gas B. And then your inhalation anesthetic could be gas C. So this three gases creates a pressure onto the surrounding and on each other. So this is called partial pressure. And this partial pressure is equal, total partial pressure is equal to the volume of all three agents. Okay. Whatever three gases, the total partial pressure is equal to A, B, and C. Okay. Now, from this partial pressure gas mixture is proportional to the volume which is. So here, when the blue color agent is high, it is the PA is high. But if the green agent is high, it is PB is high. And in third, say isoflurane agent is high, PC is high. So partial pressure is depending upon the volume or the proportion of that particular area which it has. So the important point is from partial pressure, we can identify the volume or the percentage of the agent. Okay. So it is proportional to the volume of that mixture at that particular temperature. So from partial pressure, which is measurable, we can identify the concentration of that particular vapor. I'm again give you an example how it is important and how it is helpful. So let us look at the water vapor in air at 20 degrees centigrade. Okay. The water vapor partial pressure is 6.2 kPa. So the percentage of water vapor in the atmosphere at 20 degrees centigrade is 6.2%. Okay. So at 20 degrees centigrade, at 1 atmospheric 100 kPa, water vapor occupies 6.2% of the total gas mixtures which is there in the surrounding around us. So from this, since we know the saturated vapor pressures of various agent which is available, like sevoflurane has 21%. Okay. So the percentage concentration at this particular temperature would be 21%. Now, at this point, we know that what do we need? Okay, before going forward, again, I'll stop and discuss the 3 or 4 physical principles which we have understood. One is a critical temperature. Critical temperature is a temperature above which the liquid remains in the gaseous form. Saturated vapor pressure at particular temperature, and when the saturated vapor pressure equals the atmospheric pressure, that temperature is called boiling point. From vapor pressure, we know the partial pressure, and partial pressure we can identify the volume of particular agent in a container at specific temperature. So with this understanding, now we understand that we can generate known concentration of a vapor in a carrier gas. So when you pass a carrier gas through any container, we can identify the known concentration of that particular agent. So if we are passing say oxygen through a container which has a sevoflurane, which will have a 21% of concentration. So it can carry up to 21% of sevoflurane in that particular gas, carrier gas. So sevoflurane can generate up to 21%. But now we know that what we want is just a 2%, because that is a MAC value of sevoflurane. So say on around we want the 2%. So how do we achieve that? So to achieve desired concentration, when we are passing carrier gas through any particular vaporizer, okay, only some amount will pass through it. Okay, only some amount will pass through it, and that is called the variable bypass. So if you have heard word called variable bypass, the reason to get variable bypass is that sevoflurane generates very high concentration of vapor, and we want only a smaller concentration of vapor. So we allow only small part of that particular gas to pass through. How does it work? A carrier gas routinely passes through here. Suppose if we switch dial to say 1%, what will happen? A splitting valve, this is a splitting valve, will open up, will allow some gas to pass through vaporizer chamber. Okay. This would be roughly, just for an example, not exact, but just for an example, if you want 2% concentration, it will pass only 10% of flow through this vaporizing chamber to take the gas, so that the output is 2%. Okay. If you want more, like dial we have converted to 4, then we'll allow the splitting valve, will allow more gas to pass through the vaporizing chamber. So this is how variable bypass vaporizer will work. And that is our modern vaporizer. The purpose of vaporizer is to pass fresh gas flow in a way that output of the vaporizer deliver the set concentration which we have set, or which we desire to pass. The modern vaporizer, there are some very important characteristics which all postgraduate residents should remember. I'll explain what are those characteristics and how it works. So they are flow over vaporizers. So basically, the carrier gas passes over the liquid, and then there is an open surface where there are a lot of vapor is formed, and it takes that vapor with it. It is a variable bypass. That means some gas passes out without going through the chamber. Some gas will pass through the chamber and take the inhalation anesthetic. Now, every time whenever inhalation anesthetic is taken over, new inhalation anesthetic will form. As we know, it has a kinetic energy to come out, so it loses kinetic energy, which is always in the form of heat. So the temperature of liquid will go down, and we need to have a mechanism by which it compensates for the temperature drop. They are not in our main circuit like Bain circuit or in that circuit. It is inside the anesthesia machine. So outside the circuit, I'll show you the importance of that. And they are agent specific. So these are the few important characteristics of the modern vaporizer. So if you have to identify and if you have to classify vaporizer, we can classify on the basis of 5-6 main important characteristics. One is method of vaporization. First is flow over, which we already seen. There are some of them which are bubble through, and in some there is a direct injection of vapor into the carrier gas. Okay, these are the 3 types of vaporization system. Method of regulating output concentration, one is variable bypass. Second is a measured flow. I'll explain how measured flow works. There's one older version of vaporizer which has a measured flow, and some new also has a measured flow. Temperature compensation, one is thermo compensation, second is through supplied heat. The resistance, what do you mean by resistance? When the vaporizer, our modern vaporizer, are called the plenum, or which has some resistance. So you will require a carrier gas which is slightly higher than the atmospheric pressure, which is happening in our circuit. We supply the oxygen at the pressure which is slightly above the atmospheric pressure when it passes through the vaporizer. So that's a plenum vaporizer. Low resistance vaporizers are the vaporizers which are the older versions of vaporizer, which we can even connect it with the our ambu bag and give anesthesia, which we used to give when we started our anesthesia practice, or in the field, or in the in the battlefield and in the war zone, where we do not have modern anesthesia machines. And when some anesthetics were given with the help of ambu bag, they were using low resistance or draw over vaporizers. So those who are a plenum or a higher resistance vaporizer will require not in the circuit, in the anesthesia machines. While most of them which are low resistance can be inside circuit like our ambu bag or any other anesthesia circuit where you don't have anesthesia machines which gives you a pressurized version of gas. And of course, some of them are agent specific, some of them, the older versions were used for the multiple agents also. But for the safety purpose, we want agent specific. Now, as a postgraduate, your teachers might have used these older versions of various vaporizers, and it is important to know them to understand how it has evolved. Okay. So Boyle's bottle, Goldman vaporizer, if you have any anesthesia machines, Boyle's apparatus, you might see them still. OMV, Oxford miniature, EMO, and copper kettle. I'll briefly give them in detail, but they were not accurate or not very safe. The reasons were that the Goldman vaporizer was a low resistance. That means it does not require a pressurized agent, though we can connect it to the circuit or we can put it on the anesthesia machine, but we can also use it with our ambu bag. So it was low resistance. It just draw, from the atmospheric air can also be drawn in, or any other oxygen can be drawn. There is no temperature compensation. It was a flow over type of a vaporizer where some agent will pass through it, some will bypass. So it was a variable bypass. It can be used inside the circuit or outside the circuit. It was mainly designated for the halothane. Okay. So can we use it for isofluorine? Those who have worked in a private practice in the older time when we switched to halothane to isofluorine, some of them have used it. Now let us understand, we'll understand here the vapor pressure and we'll understand how we can and how and why we can use it. The vapor pressure of halothane is 32, vapor pressure of isofluorine is 33. So it generates similar type of vapor. So when we put it on 1, it will deliver the concentration, which, 1% if we want it that way. Because the vapor pressure is same, we maybe use or we can use probably isofluorine in the Goldman bottle. Can we use sevofluorine? Some of them actually put sevofluorine also into it. The vapor pressure is very low and the concentration requirement is very high. You cannot use sevofluorine in Goldman vaporizer. Very simple reason, because the vapor pressure is different and quite low compared to halothane and isofluorine. Boyle's bottle. I think those who have seen the Boyle's apparatus this was part of the anesthesia machine when it was invented in 1917. So if whatever Boyle's bottle, if you see on your anesthesia machine today, the Boyle's apparatus, it was the one object which was there in 1917 when the first time Boyle's machine was introduced. Okay. So it was added also on the circuit, on the anesthesia machine, but also outside the circuit we can use it. There is no temperature compensation. When you press this funnel down, okay, it will allow liquid to pass through the ether, so it can be bubble through or a flow over. It was a variable bypass. It can be used inside circuit or outside circuit. It was mainly designed for ether, but people have used it for trilene also, though not very safe. Next was EMO, which was, I think, to me, the first machine which was having thermocompensation. So it was made by Hans Epstein and legendary anesthetist Robert McIntosh. So McIntosh, that is why EMO. Okay. Robert McIntosh also pioneer in designing this. So it was having thermocompensation. It has a flow over. It was a variable bypass. It was outside the circuit. Okay. It was again agent specific, but multiple agents can be used through it basically. Though it was agent specific, but multiple agents were used through this particular device. Mainly it was designed for the ether. Next is copper kettle. I don't know. I have just seen one when I was in my residency. So copper kettle was something which was actually was used through the inside the anesthesia machine. So it was a plenum. There was no thermocompensation. But here, as I said, variable bypass. So what anesthetists had to do was to pass specific. There was a special, line for that, which was connected to this particular copper kettle. And you pass 1 liter through this and 9 liters straight away into direct outside the circuit. And then both of them are mixed in the end. So you have to separately calculate the vaporizer, the flow which you need to pass through the vaporizer. It was again a bubble through, so the liquid, the gas will pass through the liquid. So it takes maximum concentration. It can be used on the anesthesia machine, cannot be used outside into the field outside OR. So here you have to put separate flow which passes through this copper kettle, which was heated. And then some of senior person might have seen this OMV, Oxford Miniature Vaporizer. Basically, Oxford Miniature Vaporizers was again a low resistance, so can be used outside on with the Ambus bag, but can also be fitted on the anesthesia machine. So though it was a low resistance, it could be fitted on the anesthesia machine. It has a thermocompensation. Now, thermocompensation, I'll explain you how modern vaporizer works. But here there was a liquid jacket was there, of anti-freezing agent. So there was an anti-freezing agent outside the, in the outer wall, which will prevent the heat loss. There is a flow over with metal beaks, variable bypass, and other things. It was agent specific, but multiple agent could be added. And for each agent, there is a specific numbering was given. So if you are using isofluorine, you use this number. If you are using, some other enfluorine, you use this agent. Some sort of such system was there in this. It was a very small bottle, 50 ml bottle, which you can easily carry. So this is about some part of history, which might be important for you in your exam. Okay. So on the basis of this technique of vaporization, regulating the output, temperature compensation, resistance, position of vaporizer, and specificity, we can identify and classify the modern vaporizer. So modern vaporizers are mainly two. One is variable bypass, and in some other system, there is a measured flow which passes through this particular vaporizer. Variable bypass can be a plenum vaporizer, one, or second plenum vaporizer, which has something called the electronic control. Okay. Measured flow or the desfluorine vaporizer is not, though there is a variable bypass, but basically it is a measured flow which is added to the circuit. So desfluorine vaporizer and DIVA are sort of a measured flow type of vaporizer. Okay. Now let us again go back to the variable bypass system. So in the variable bypass system, if you have switch it on, if it is on the 0, that means entire gas will pass through the bypass system. When you switch it on, the splitting valve, this is called the splitting valve. The splitting valve will open up and will allow some gas to pass through the vaporizing chamber, which will take away these agents which are there into this vaporizing chamber. You lower the dial concentration. When you do lower the dial concentration, small amount of gas passes. If you increase the dial concentration, splitting valve goes up, less gas passes through the bypass, more gas passes through the chamber. So this ratio of gas flow that goes through vaporizing chamber and fresh gas flow gas which passes through the bypass pathway is called splitting ratio. Okay, very important terminology, splitting ratio. Now this splitting ratio is fixed. Okay, and it is again based on the vapor pressure. This is the splitting ratio for each particular agent, and it based on two things. One, what is their saturated vapor pressure, and what is the end-tidal sevofluorine, isofluorine concentration which we want. So the vapor pressure might be same for the isofluorine and halogen. But the splitting ratio will be different because we want a different n-tidal concentration because their MAC values are different. So it is based on their requirement. Okay. So sevoflurane splitting ratio is 25:1. The modern vaporizer, which we have isoflurane, sevoflurane is the agent. The splitting ratio of isoflurane is different than the splitting ratio of sevoflurane. That is why our vaporizer are agent specific. You cannot use sevoflurane in isoflurane vaporizer or isoflurane in sevoflurane vaporizer because their splitting ratios are different and the output concentration, even if you put 1% diol concentration, you will receive a different type of output. Okay, so they are agent specific. Very, very important understanding. Now you just realize that a lot of gas flow passes through this particular chamber, in this vaporizing chamber. Now there are three things happen. One, the temperature will drop because it will take the agent, the new vapor will form, so the temperature will drop. Sometimes when you give positive pressure, a back pressure can come back from here. That will also have its influence. And when a gas passes through this particular chamber very fast, or if you keep higher flow, it may not have enough time for the vaporization. So these are the three important problems which we will have to solve to get the accurate output. There are three important problems which we have to solve to get the accurate output. And how these are solved in our vaporizer we'll understand next few slides. So if you do not have adequate surface for vaporization to occur, what they've added was additional wicks. Okay, they've added additional compartments, and over compartment they have kept a wick type of substance which will take the liquid into its particular into its part, which can be converted into the vapor. So what they have done, they have basically increased the surface area. So by increasing the surface area, even at higher flow output, set output can be achieved. Suppose if you put 8 liter flow and 8% sevoflurane concentration for the inhalation induction, it still should make output of 8% by increasing the surface area. Okay. So by addition of wicks and the compartment, it increases the surface area. Now, the vaporization reduces the temperature because we have understood that what it requires is a energy. And when the vapor is formed and which is taken away into the gas, new vapor is formed. So the temperature drops. The molecules which requires change from liquid to vapor, they require energy, and this amount of energy which is required is called the latent heat of vaporization. So what is latent heat of vaporization? Amount of calories needed to convert a unit mass of 1 gram of liquid into the vapor. Okay. So for each gram of liquid turned into the vapor, a heat is lost. Now, when heat is lost, we know that the vapor pressure is a temperature centric. So if temperature of liquid goes down, what will happen? The vapor will drop. The vapor pressure will drop. The volume of vapor will drop and the concentration will drop. So we need to develop a mechanism which controls or maintains the temperature inside. Okay. So what they have done, there are two things which can be done. One is the wall which was created earlier. If you see, glass bottles were there. Then they started making the metal wall. And we need a specific metal which can absorb the atmospheric temperature. It can store and transmit atmospheric heat to the agent. So we need a metal which can absorb, store, and transmit. Okay. So we need a metal which has high specific heat, so which can easily transmit, and it can have a high thermal capacity. It can store and send it to the liquid. And there are three main metals which are identified. The best one is actually the copper. Copper, bronze, and SS, these are three metals. And most of the modern vaporizers are made from the copper because it has a high thermal conductivity and high what you call a capacity to store and transmit into the liquid. Now, only this, putting the metal may not be helpful. So what they have done was to add a automatic temperature compensating valve. Okay. Metal with higher specific conductivity may not alone be sufficient. So what they've done, they've decided that we can add the flow. So if the temperature of liquid is getting dropped, so the vapor pressure will drop. So we have to change the flow which is passing through the chamber versus bypass. So to do that, what they add is called temperature compensating valve inside the vaporizer. So temperature drops, it allows more gas to pass through the chamber. Okay. And the temperature compensating valve are of three technology. One is metallic rod. Okay. Second is a liquid crystal bellow, and third is a bimetallic strip. So metallic rod, which contracts or expands with the temperature, which is part of a Draeger vapor series. So metallic rod, the metal which can easily contract and expand with the temperature. So if temperature drops, this constrict, we know it shrinks. It allows more flow to pass through the chamber. If temperature increases, it expands and it will allow less flow to pass. Okay. The second is called liquid crystal bellows. The liquid is mainly ether, okay, or freon. So this liquid, ether or freon, will contract with the reduction in the temperature, which will allow a larger flow to pass, okay, through the chamber. So that's a liquid crystal bellow, which is not used in the modern vaporizer. It was mainly used in the EMO vaporizer. Okay, the EMO vaporizer which you have seen. The liquid crystal bellows were used in the EMO vaporizer because over a time it can fracture, the liquid can be lost, and some other problems were there. So it is not used now. What used in most of our tech vaporizer is called the bimetallic strip. Now, the bimetallic strip concept is like this. There are two metallic strips. One is iron and second is nickel. Now, both reacts differently with the temperature changes. Okay. One metal expands or contracts more than the other. Okay. So let us see, the iron expands less, nickel expands more. Okay. Just for an example. So when temperature rises, both increases, but one increases more than the other. Then what they have done, they have tied them together. Okay, they have tied them together. So now when temperature changes, there is no way they can increase or decrease. So they'll bend because they are tied together. So they've allowed a bending inside, which I'll again show you how it is worked. Okay. So iron and nickel, it is called INVAR. Okay. Here is a bimetallic strip, which is covering an opening. If there is a temperature drop, okay, it bends because one contracts more than the other, which will open up this opening and allow more gas to pass. So this is part of most of our tech vaporizer where there is a bimetallic strip. This is just again for the temperature compensation. So we have seen two techniques. One is this valve which allows more or less flow, or the metal wall which takes atmospheric heat, store, and then transfers inside into the liquid. Now, because of sometimes for the positive pressure, okay, with the positive pressure, the back pressure can come. Okay, this back pressure can come, and then it can push this gas into the bypass and increases the concentration. So to avoid that particular point, what they've increased was to increase a pathway, which was a back pathway. So this pathway is now much more longer. So even with the pressure, it will not reach right down to the splitting valve. So now our modern vaporizer are variable bypass, agent and concentration calibrated. That means there is a splitting ratio which is fixed with that splitting valve. It is flow over, it is temperature compensated, and it is back pressure compensated. So this is the characteristic of our modern vaporizer. So there are various type of vaporizers: variable bypass, flow over, temperature and pressure compensated, concentration calibrated, and agent specific. Vapor one is from the Draeger company, which, as I said, is using this metallic valve, okay, metal rod for the compensation, while tech vaporizer are using this strip, okay, two metal strip which can bend. So these are the what do you call it, Draeger and tech vaporizer. So we have seen first the plenum one. Now we'll see plenum with the electronic control. Okay. So which are the electronic control? If anyone has heard something called the Aladdin cassette vaporizer, which is part of a one anesthesia machine. So Aladdin cassette has two things. Okay. One is something called the cassette, dumb cassette. That means in this cassette, they get the liquid. Okay. And then there is a control unit. Okay. This is the liquid tank. And then this is a control unit. Now, how it is different? It is a variable bypass, that is for sure. So this is a variable bypass vaporizer. Okay. Sorry, let me go back. Okay. So this is variable bypass. Now, how it is different? Where in our plenum vaporizers, there where we have to make a mechanical things inside, a bimetallic strip or a rod. We have kept a wicks. We have increased the surface area. What they are doing inside this is they are measuring the vapor pressure and the temperature. They are measuring the temperature and vapor pressure, and on the basis of vapor pressure and the temperature available, they are giving this information to their computer to increase or decrease this variable bypass. So it is basically an electronic vaporizer which has a temperature and pressure sensors inside the chamber, which informs the computer and which alters the bypass flow. Okay, so that's a plenum electronic control vaporizer, which is allowed in cassette. Now let us look at the desflurane vaporizer. Okay, so we have seen that when temperature increases, there is increasing in the saturated vapor pressure, and temperature at which saturated vapor pressure equals the atmospheric pressure is a boiling point. Okay, that's your boiling point. Now, when you look at the boiling point of desflurane, it is just 22.8. Now, when it is 22.8, which is, the operation room pressure or any other atmospheric pressure, the moment temperature goes slightly up or down, the vapor production is, varied differently. It becomes unpredictable and variable even at room temperature because of very less boiling point. The other agents has boiling point much more than what the atmospheric temperature or room temperature is. But the desflurane boiling point is right at the room temperature, and slight change creates a lot of problem. So what they have done, they electronically heat the desflurane vaporizer. That is why desflurane vaporizer requires put it into the electric socket and heat it. Okay, you connect it. It will take some time to heat that vaporizer chamber to 39 degrees centigrade. Okay, it takes it to 39 degrees centigrade. So at 39 degrees centigrade, the gaseous pressure is actually 2 atmospheric pressure or 200 kPa. So it makes 200. So now it is heated at 39 degree constantly. The vapor pressure is quite accurate. So then this vapor is directly added into the fresh gas flow. So this is a circuit diagram of a desflurane vaporizer. And there are, in this particular area, electronically heated vapor is produced, which is a fixed, vapor pressure, and then the vapor concentration is produced by electrically heating. Now, this particular point, differentiating pressure value, is very important. When you make dial say 2%, so fixed amount of vapor will be added. But suppose if you increase flow from 4 to 6, how does it identify? Because if we do not have any mechanism to identify difference in the flow, it will constantly give only same amount of vapor, which is not accurate, because with increasing flow, you need slightly more vapor concentration. So differentiating pressure transducer here actually identify the flow and accordingly increase or decrease the output of vapor from here as per your dial concentration. So it is very, very important. These are two components. Okay, one is this differentiating pressure transducer and this valve, which creates the vapor, exact vapor concentration. And then it is injected. So, desflurant vaporizers are electrically heated, thermostatically controlled. It has a constant temperature and pressure. Electromechanically coupled. So, electromechanically coupled dual circuit gas vapor blender. So, it is a gas vapor blender. Now, three important points. Selector tech system. Okay, selector tech mounting system. Now, earlier, in that bar separators, we actually were putting multiple vaporizers. But sometimes after we have ether, halothane, and then we adding isofluorine and then sulfurine, there's not enough space. So a system was added, which is called selector tech mounting system, which has a fewer mounting locations, and the vaporizer designs were made in a way that you can remove one vaporizer and put another vaporizer even during the procedure or surgery. And when you put it on this particular point, it presses this particular area. Okay, this particular area it presses, and when it presses this area, it opens up and the gas passes through the vaporizer and comes back through here. So this is how a selector tech system works. Also, it gives you an advantage that with that system, there is an option of something called the interlock. So the moment you make it on, okay, you make it on, you cannot turn the dial. That's a safety system. When you make it on, then only you can turn the dial. And when you rotate and start the vaporizer, observe this carefully, this part, it comes out. Okay. So when you turn it on, this moves, and this movement, okay, will prevent other vaporizer to work. So only one vaporizer can be used with the interlock system. Only one vaporizer can be used. You cannot use two agents simultaneously, which is absolutely a wrong technique. Now, a word about desflurant vaporizer in Alauddin cassette. So in Alauddin cassette, it is still a variable bypass type of a vaporizer. The reason is that it is still measuring pressure, vapor pressure, and temperature. So Alauddin cassette is more or less similar to the variable bypass. Okay. It is a plenum with electronic control desflurant. It does not require a separate heating. It just measures the vapor pressure and temperature and accordingly vary its flow through the bypass chamber and the vaporizing chamber. There is something called DIVA type of a vaporizer, which is again a measured flow. There are two, devices where it is used. One is, I think, juice machine and one is Maquette machine. These are the two vaporizers where actually what vaporizer does is that liquid agent is, made into a vapor. It goes into a, dosing chamber, then goes into the vaporizing chamber where vapor is made from that fixed amount of liquid. We know 1 ml of liquid produces this much of vapor. So it is in the vaporizing chamber, vapor is made and exact amount is injected directly into the circuit. So this is direct injection of volatile anesthetic agent. Of course, it is converted into the vapor and it knows that exact amount of vapor which is made with each volume, which is of liquid. and then it is added into the circuit. This is called direct injection of volatile anesthetic. A brief information about various vaporizers. So what are the current vaporizers? Tech series. Tech series has 2, 3, 4, 5, 6, 7. Most of us has 6 or 7 vaporizer. Draeger has similar type of series, 2000, 3000, and D would be for the desfluran. Panlon Sigma also has various, and the alpha is for the desfluran. There's some other companies, and there are much more companies. As again, I'm saying, I'm not promoting any particular company. All vaporizers are good as far as you know how it works and what are the features of that. So Tech series is sort of one which was used since a very long time, 2, 3, 4, 5, 6, 7. 7 is the current one. I'll briefly take you, there is a very good Tech series evolution paper, and there is a very good table there. You can go through it. So Tech 2 was having inaccurate flow, okay? And there is a problem of pressure, back pressure, pumping and tipping was there, and it was leaking in off. 3 was better at lower flow. The 2 was inaccurate at lower flow. It was Tech 3, they improved accurate at lower flow. No pressure or pumping, tipping, no problem, but there's still small leak. The volume was actually less, okay? And the rotation was, more 180-degree rotation of the dial. Tech 4 added the baffled system, which we understood, the compartment and the weeks. It avoided tipping problem. Then we realized that turning dial clockwise was actually hazardous. So we actually started making it counterclockwise. So dial was turning clockwise earlier, then it started doing counterclockwise. Interlock was added. It was single-headed use, and the volume was increased to 125. Tech 5, we started making counterclockwise. Okay, the dial is turned counterclockwise, and the volume was increased to 300 ml. Tech 7 has all the system which we have discussed. What are the features which we have discussed is all part of Tech 7. Helical system, baffled system, dial turn counterclockwise, single-handed use possible, no calibration required. Earlier required calibration at this different interval, and the volume has increased to 300 ml. So Tech series evolution, baffled system added, increased length of tube leading to the vaporizing chamber. So pressure and pumping tipping problems were reduced. Vaporizing chamber volume were gradually increased from 75 to 300 ml. Dial problems was gradually solved. Rotation turned from clockwise to counterclockwise. And without locking vaporizer on the bar, you cannot turn the dial, which I showed. So you just cannot put the vaporizer in the start. You have to lock it, then only you can turn the dial. Earlier, frequent calibrations were required. Now it is permanent. You don't require calibration for Tech 7 newer versions of vaporizer. Interlock system were added, and the filling system were added to improve inadvertent filling of a wrong agent, which we'll discuss after 2-3 slides. So Panlon Sigma series delta is similar to Tech 7, and alpha is for desfluran. Draeger Vapor 19 series is Tech 4-5, while 2000 and 3000 series is like 6-7. Filling system, as I said, earlier was a funnel filling. So you open the vaporizer opening and directly pour the liquid with the help of a funnel. But then we realized it was creating problems. So we started making agent-specific designs where you cannot put wrong agent into it. And then the leakage and the atmospheric leakage and the loss is also not there. So one was a keyed filling. Okay, this was a key which was made. Then came the easy filling where you can fill it on the bottle, and the bottle will fill the appropriate, cap only because of their, arrangement on the neck of the bottle. So that was the easy. And then what we added was a quick filling system. Okay, quick filling is a direct bottle which is now fitted onto the sevofluran chamber opening, which is gravity field closed field system for the sevofluran. While for the desfluran, if you have used desfluran, it requires pressure and a very tight zero leak valve, which is there. The reason is that the moment it comes in touch with the atmosphere, it immediately turns into the vapor because of very low boiling point. So it really requires a zero leak type of a system, which is there for the desflurane vaporizer filling system. Last slide. How to calculate the liquid agent the vaporizer uses per hour. So this is calculated on the basis of Unbreath-Eisencraft formula, which calculates 3 into the fresh gas flow which you use and the dial which you have set. Okay. So this will tell you ml of liquid used per hour. Now this formula is based on one assumption that 1 ml of liquid typically forms around 200 ml of vapor. Okay. Now, halothane makes 229 ml, isoflurane makes 195 ml, sevoflurane makes 184 ml, and desflurane makes 210 ml. So generally, it is around 200 ml of vapor is made from 1 ml of liquid. Okay. So if you set 1 ml dial, 1 liter fresh gas flow and 2% dial concentration, okay, what you will use for isoflurane is a 6 ml. If you sevoflurane dial it slightly higher would be 8 ml and desflurane would be 13 ml of volume. And then of course you can calculate the cost from that particular point based on the purchase price which you have in your institute. So you can easily identify the ml of liquid which is used from the vaporizer based on your dial concentration, dial which you have set, and the fresh gas flow which you have used. Okay. It's not that they are still not there are hazards are not happening. Incorrect agent is still giving. Some of them are not tipping proof, so you cannot tilt it. Okay. Some of them has a T mention on the dial. If you see T, that is for the transport. So when you are transporting vaporizer from one machine to other machine, you have to actually put it on the T. And then when you put it on the T, you can easily transfer without tipping it into the anesthetic chamber or a bypass chamber. So tipping can still occur, overfilling occur, reverse flow can occur, leaks can occur because of O-ring, because of improper fitting. You are not giving this simultaneous administration more than one vapor, but sometimes in the older anesthesia machine, if you have a back bar where you have mounted two, you can do it. Vapor leak, contamination, obstruction of fresh gas flow because of your improperly pushed your vaporizer, interlock malfunctions. These are some of the problems which can occur with even your modern vaporizer. So you have to be extremely careful while using the vaporizer. And one of the most common hazard of vaporizer is empty vaporizer. You have to check every day in morning when you come whether vaporizer is completely filled or not. So if you do not have agent monitor, you will never know that vaporizer has become empty and you're not giving any anesthetic agent. So empty vaporizer is one of the most important problem which you can occur. Now, one important understanding. Now we know that when you go to a higher altitude, your flow which passes through your anesthesia machine can change because of higher altitude. The pressure drops and it depends upon the viscosity, and that is why the flow would be higher than the usual. Does it happens with the vaporizer output? Now vapor production depends upon saturated vapor pressure, and it is inversely related to barometric pressure because it is at specific temperature and atmospheric pressure, which would be lesser, right? But its clinical effect depends upon the partial pressure, which is the product of volume percent multiplied by the atmospheric pressure. So I'll just explain. At 6 liter flow, dial of 1%, 60 ml of vapor is produced at 760 milligram. That is 1 atmosphere at the sea level. So 1% output at 760 milligram is 7.6 milligram of partial pressure. Now at say 10,000 feet altitude at 500 millimeter of mercury pressure, which is lesser, the vapor which is produced is 113. Okay. Here 60 ml of vapor, here the vapor is produced more. The output would be 1.8%. Okay. The output would be 1.8%. But at what pressure? 500 mm of Hg. So partial pressure in the alveoli would be only 9 millimeter of mercury. So let me take out this. At sea level, 1% volume at high 10,000 feet altitude, it gives 1.8%. So the changes is 180%, but the partial pressure changes are less, which is the main way or the parameter which is used, which is utilized in the lung to transfer the agent, is not very high. It is just 7.6 to 9%. It is not increasing by 180%. It is only increasing by 108%. So there is not a gross changes for the dial concentration even at high altitude, though your flow may change. At high altitude, your sevoflurane vaporizer will not be affected much. It will be, there will be a slight effect. So that takes me to the conclusion that we have many different type of vaporizers. You should really understand how they work to use them safely. Of course, modern vaporizers are relatively more safe, but you still need a very close observation for proper use to use it safely. Thank you very much. And at the end, again, as I said, I would invite you to a very important event, that is NAC 2026, which is combined with an international meeting, International Airway Management meeting. And we have a very important something called the Well Lead Award. Well Lead Award is a part of International Airway Management meeting, and it has a prize pool of $1,900 US. The first prize in the 4 category is $400 US each. And not only money is important, it is also important that those who are selected for Well Lead will be get chance to present in front of more than 30 international faculties of well-known repute who has already committed their physical presence here. So I invite all of you to showcase India's strength in airway to the world. Thank you very much. Over to you, ma'am.
Yeah, thank you, sir. Thank you for a very enticing talk. I now request Adarsh Swami Chandra Swami sir for a vote of thanks.
Yeah, Dr. Amit Shah, it was.
Is there any?
Yeah, you would want some questions?
Sir, please.
Dr.
Yeah,
Amit?
if there are any questions we need to answer, we can do that. If there are any, Kashish.
Yes,
I
there are no
don't think there
questions.
are any.
Yes.
Yes. Yes, Adarsh sir.
Yeah, actually, it was so well covered. I don't think people would they would actually be engrossed whatever they have heard. And as you said, I am really fortunate that I have been through Ether era, Trilene, Ether, and Goldman, and EMO. And today we are using Aladdin cassettes. And this has been so well covered that I think all the students going to take the exam, they would be so well versed with the concepts, the physics, and the other concepts of these vaporizers. Dr. Amit Shah was really well covered. I would like to thank you. It has been a great talk, not only for the students, even for me. I'm really thankful.
Yeah, true, sir.
Thank you,
It
sir.
was
Thank you so
truly, it was so beautifully explained that there's such a complex topic in such a simpler and beautiful way. Thank you, sir.
Thank you so much.
Thank you so much, sir.
Thank you for the kind words. It was really heartwarming to talk to all of you, and the concept which I have really, it's close to my heart, I could explain it to you. I hope that all of them had, cleared their doubt if they have any. Thank you.
Thank you, sir.
Thank you.
Thank you
Thank you,
so
Dr.
much.
Akil. Thank you, Dr. Mamta. Thank you, Dr. Adarsh.
Thank you so much, everyone. And we have not received any questions from our delegates till now. So, once again, I thank each one of you for participating with us today and for being here with us. Clarnet is really proud to host all of you, and I would just love to host you all again in the near future. Thank you so much.
Thank you, everyone.
Thank you all. Bye-bye. Bye-bye.
Good night. Thank you.
Thank you.